Hi guys, welcome to the run through of the differentiation test. So let's go straight to the 3 questions, 1, 2, and 3. Go through each of them in 10. And if there's any questions, make sure that you make a note of them so that you can ask me later on. All right, question 1. Given that y is equal to cos 2 theta over 1 plus sine 2 theta, where theta is between minus pi over 4 and 3 pi over 4, you've got to show that the differential dy by d theta is equal to a over 1 plus 2 sine theta, sine 2 theta, where a is a constant to be determined. 4 marks, nice and easy. Start with y is equal to cos 2 theta over 1 plus sine 2 theta. You can see that we've got a fraction here, therefore we are going to be using the quotient rule. Now don't worry if you don't remember the quotient rule, because in your formula book, which is on the screen now, you can see the quotient rule as it is. So we've got some function of x divided by some function g of x. It's the differential of the bottom multiplied by the top minus the bottom multiplied by the differential of the bottom, all divided by the bottom function squared. So bot d top minus top d bot, all over the bot squared. So let's get into that. First of all, it might be useful for us to note down what those functions actually could be. Now I prefer using them in terms of u and v. So I'm going to have down my u as cos 2 theta, seeing as that's the function on the top. My du by dx is going to be, well, the differential of cos using the chain rule, sorry. That 2 is on the inside, 2 theta, differential will be 2, so it's going to be 2 loads of the differential of cos. Cos goes to minus sine, so it's minus 2 sine 2 theta. And my other function, the v, is equal to 1 plus sine 2 theta. Well, it's going to be the same sort of idea. When I differentiate that, 1 will go to nothing. So I'm going to have dv by dx. The 1 goes to nothing. The sine 2 theta is going to be going to 2 cos 2 theta, again using chain rule. Okay? So this is our starting point. We've got the things that we're going to refer to later on. We've got the top, cos 2 theta, d bot, minus 2 sine 2 theta, and the bot, 1 plus sine 2 theta, and the d bot, 2 cos 2 theta. So let's put that in. dy by dx is going to be equal to the bot. Well, the bot was 1 plus sine 2 theta multiplied by d bot. Okay, so that's going to be our minus 2 sine theta. 2 sine 2 theta. Minus top, cos 2 theta, d bot, 2 cos 2 theta. Okay, all divided by the cos, by the bot squared. 1 plus sine 2 theta, all squared. All right. Let's expand these brackets and simplify them out a little bit, because if I look at that first bracket, I've got 1 load of minus 2 sine 2 theta, so I'll put that in first. Minus 2 sine 2 theta. And then when I do 2 sine theta times minus 2 sine theta, I'm going to have minus 2 sine squared of 2 theta. Next bit, I've got to multiply these two together. Cos 2 theta multiplied by 2 cos 2 theta. I'm going to have 2 cos squared of 2 theta. All over 1 plus sine 2 theta squared. Okay, great stuff. Now, hopefully, after you got to this stage, you might notice that we've got sine squareds and cos squareds. Now, if I factorize what's there, I could take out this 2 that is missing there. I have the minus 2 sine 2 theta, and I could spot that here, this is minus 2 loads of sine squared 2 theta plus cos squared 2 theta. Notice that because I took the minus 2 out, this minus 2 is out, and that minus 2 is also out, leaving us with a positive. Still all over 1 plus sine 2 theta all squared. Okay. Well, what does sine squared 2 theta plus cos squared 2 theta become? Well, any sine squared of anything plus the cos squared of the same angle, we know becomes 1. Sine squared a plus cos squared a is 1. So therefore, that's what we're going to get. We're going to have here, this ends up becoming minus 2 sine 2 theta minus 2 times 1. So just minus 2 over 1 plus sine 2 theta all squared. And then you might think, well, what else can I factorize from the top? You can see that both of these are in terms of 2. So if I try taking out that 2 again, but even better if I take it out as a minus 2, I could write that as minus 2 into sine 2 theta plus 1. Or even better than that, because if I look at what the denominator is, the 1 plus sine 2 theta squared, you might spot that these are the same. So instead of writing it as sine 2 theta plus 1, I'm going to put the 1 at the front. 1 plus sine 2 theta. Because now I can see that there's an algebraic factor that can be cancelled. Okay, so I'm going to cross this one out, and that's going to cancel with the squared at the bottom. That's going to now leave us with a minus 2 on the top and a 1 plus sine 2 theta on the bottom. And if I go back up to what the answer wanted, because I can't see anywhere else I can go with that, the answer said that we wanted dy by d theta. I think I've put d theta, I've written dx. That's just d theta. As a over 1 plus sine 2 theta, where a was some constant to be determined. We've done it. We've written it in the form a being minus 2 over 1 plus sine 2 theta as required. Job done. Okay. The second question. The curve C has equation y is equal to 3x minus 2 over x minus 2 all squared, where x is not equal to 2. X is obviously not equal to 2 because you can't have the denominator of a fraction being equal to 0. And if that were equal to 2, 2 minus 2 would be 0. It says the point P on C has x coordinate 3. Find an equation of the normal to C at the point P in the form ax plus by plus c equals 0, where a, b, and c are integers. Okay? This is a classic P1 question. We've been doing questions like this since P1, where we've been working out the equation of a tangent or a normal. So we know that the first thing we're going to need is a coordinate, a full coordinate. I've got half of the coordinate, so I've got the x coordinate. So when we've got this x coordinate of 3, as is stated in the question, I need to work out what y is going to become. Well, y is going to be what we get when x is 3. So 3 times 3, which is 9, minus 2 over 3 minus 2 all squared. So therefore, 9 minus 2, we've got 7 over 3 minus 2 is 1. 1 squared is 1. Don't need to worry about that because dividing by 1 doesn't do anything. In other words, our coordinate is 3, 7. Okay? X coordinate 3, y coordinate 7. The other thing we need for working out the equation of a line, i.e. this normal, is we need to make sure that we've got a gradient. And in order to find out the gradient, we're obviously going to need to differentiate. Sorry if you can hear the ambulance and the fire brigade out there. We're going to need to work out what the dy by dx is for here, the gradient at any point. Okay, so that's what we're going to deal with. So we're going to have y is equal to 3x minus 2 over x minus 2 all squared. And same as before, we're going to have to use the quotient rule in order to differentiate that. So in order to differentiate that, I'm going to establish my u's and v's. My u is going to be the top part of this. Let's move that over a bit. There we go. So I've got space. So now I've got u is equal to the top, 3x minus 2. Du by dx is equal to 3. V is the bottom. It's equal to x minus 2 all squared. dv by dx is therefore, well, we're going to have to use some chain rule on that. First of all, differentiate the bracket. So the 2 is going to come down to the front. And we're going to have this is equal to 2 loads of x minus 2. Dropping that power of 2 down to 1. And then we're going to multiply by the inside. Multiplying by the inside, x minus 2, the differential of that is 1, so I'm going to multiply this by 1. It doesn't change anything. So our differential is as such. Okay, so there we go, we've got that bit. Now using the quotient rule as required, dy by dx is equal to, as we know, bot to top. So the bot, which was x minus 2 all squared, d top, which was 3, minus top, 3x minus 2, d bot, which was 2 into x minus 2, but we'll simplify that a little bit further, make that 2x minus 4 to save us some time. So 2x minus 4 in there, all divided by the bot squared. And the bot squared is going to be the x minus 2 all squared, but when you square a square, it becomes to the power of 4. Right, you could spend some time trying to deal with the algebra here and trying to simplify that. However, I do not recommend it because chances are, A, you might get it wrong and then get a wrong answer, and B, it's going to take a long time and it might just be too tricky. Because we know what we need to do with this. We've got an x coordinate. All we need to do is plug our x coordinate into this. If I know that when x is equal to 3, I can find the gradient of the tangent. Remember, that's what dy by dx gives us, the gradient of the curve and therefore the tangent at any point. Plug x in. And we're going to get 3 minus 2 all squared multiplied by 3 minus 3 times 3 is 9. 9 minus 2 multiplied by 2 times 3, which is 6 minus 4 over 3 minus 2 to the power of 4. Okay, so let's look at what they all give us. 3 minus 2 is 1, so I'm going to have 1 squared multiplied by 3. Minus 9 minus 2 is 7. 6 minus 4 is 2. All over 3 minus 2 is 1. 1 to the power of 4 on the bottom. Now think about the things that aren't going to make a difference. Those ones aren't going to make a difference. So all I'm going to be left with is 1 squared times 3 is 3, minus 7 times 2, which is 14, over 1, which is just 1. And 3 minus 14, I've got minus 11. Okay, so minus 11, okay? We've got the gradient. But more importantly, that's not the gradient of the normal. Remember, we're after the normal. This word here, normal, where we've got the tangent. We've got the gradient of the tangent there. So that what we need to do is now change that. And remember, we change to get the gradient of the normal by doing the negative reciprocal because it's perpendicular. The gradient of the normal is minus 1 divided by the gradient of the tangent. So I'm going to have minus 1 divided by minus 11, which will just be 1 over 11. So that's the gradient we're interested in. So now what this becomes is just a situation where we're trying to find the line where our coordinate that we're going through is 3, 7. So we've got that. That's our x1, y1. And the gradient is equal to 11. And remember, the formula used, that we've been using since P1 for this, is y minus y1 is equal to m into x minus x1, where this is y minus our y coordinate, which is 7, is equal to m, 1 over 11, into x minus 3. Okay, I don't want to multiply through by an 11 because it does make things awkward. So I'm going to multiply both sides by 11. If I multiply both sides by 11, I'll have 11 into y minus 7 is equal to x minus 3. Avoid using fractions, which now means multiply the 11 here. 11y minus 77 is equal to x minus 3. And then we're just rearranging this for 0. Because remember, they wanted it in the form ax plus by plus c is equal to 0, not in the form y plus mx plus c. So seeing as x is positive on this side, I'm going to move the others over to this side. Well, I'll keep my x, move the 11y over, minus 11y, and then add 77 to both sides. And if I add 77 to both sides, I'm going to be left with 77 minus 3, which is 74. And there, ladies and gentlemen, is the answer that we needed. Okay? So, that's part 2 done. The last part. Question 3, use the identity for sine A plus B to prove that sine 2A is 2 sine A cos A. Okay? We are given this in the formula book. It is here. Sine A plus B is sine A cos B plus cos A sine B. That's going to be the first thing I'm going to write down. So when I get onto that bit, which is part A, there we go, try that again. Okay. Sine A plus B is equal to sine A cos A plus, cos B plus cos B cos A sine B. Okay, so we've now got the setup there. However, we're looking at sine 2A. Sine 2A would be the same as having sine of A plus A. So therefore, we're actually looking at sine A cos A. We're replacing the B's that we see up here with A's. Plus cos A sine A. Now, you might notice they are both the same. Sine A cos A and cos A sine A are the same because we can write it in any order because it's commutative. So therefore, adding them together, I've got 2 sine A cos A as required. Okay, so a bit of quadratic demonstrandum going on there to show that we've got the right answer. That's exactly what we needed. Now, the likelihood is the fact that they've given you that proof to start with means you're probably going to find that a useful thing in this question. So let's see. Part B. Show that d by dx of natural log of tan of half x is equal to cosec x. That notation there, d of dx, just basically means if y is equal to this, differentiate it. Because instead of having y inside the dy by dx, the d, it's differentiate this with respect to x. Okay? So what we're actually looking at in B is having y is equal to natural log of tan of a half x. Okay, so we've got a bit of a chain rule going on there. But it's tricky because it's a double chain rule. So some people may find it easier to consider this in terms of z. So I could have log of z, where z is equal to that tan a half x. And if I've got z is equal to tan a half x, I can now do dy by dz. We know how to differentiate log, it goes to 1 over z. I can also get dz by dx and differentiate the tan. Now, tan is a standard. We're given it in the formula book. Tan differentiates to sec squared. But more importantly, when it's a kx, like this one, a half x, that half is going to go on the outside by chain rule, a half sec squared of a half x. So that's what we're going to get there. And have a half sec squared of a half x. Okay? Now remember that dy by dz can also be written without the z. I can now have this 1 over, instead of z, I'm going to write what z is. Z is equal to tan a half x. So tan a half x. And now, to get dy by dx on its own, I need to multiply both of these two things together, dy by dz and dz by dx. Because remember, if I do dy by dz multiplied by dz by dx, those dz's will cancel, and I'd be left with dy by dx as required. So what I'm doing, I'm going to multiply by this 1 over tan a half x, and then multiply it by the dz by dx, which is a half sec a half x. Okay? So multiply that by half of sec of a half x. Okay, good. So now what we can hopefully see is that they have been combined. Okay? Or you could start thinking about, yeah, we'll combine them. So if I multiply them together, that sec a half x is going to go on the numerator of our fraction. So that's sec squared. No, I've not written sec squared. Over the tan a half x. But we've multiplied by a half as well. When we multiply by a half, 2 goes on the denominator. So I've got sec squared of a half x over 2 tan of a half x. Okay. Now we just need to think about how I can go about cancelling what they are. okay? Or maybe writing them separately might be easier, okay? Think of what sec is first of all. Sec is 1 over cos. So I can imagine this. We'll separate them out. We'll have the half. Take the half out. Sec squared is the same as 1 over cos squared of x. Tan of a half x is the same as sine over cos, but it's on the bottom of the fraction. So in other words, it's actually cot that we've got. That we've actually got, if you think about it, it might be easy to look at it this way. We've actually got a half of sec squared a half x multiplied by cot a half x. That's actually what we're looking at here. Sec of a half x, sec squared of a half x, sorry, cos of a half x. So if I now split them into what they actually are, I've got a half of sec 1 over cos a half x, and then cot we know is cos a half x over sine a half x. Now, don't forget there's actually a squared there as well. Now, if I think of the cancellations that can be done here, there's a cos a half x on this fraction that can cancel with one of the cos a half x down there. So I will cancel them. I'll cancel my squared. Now, on the top of this fraction in total, I'll have 1, and on the bottom, I'll have 2 cos a half x, sine a half x. But I'm going to prefer to write that as sine a half x, cos a half x. And now this is the stage where we realize why the question started with making us do the proof of sine 2a being 2 sine a cos a. Because I've got 2 sine a cos a on the bottom of this fraction, okay, where the a is a half x. So if I want to change that now to be sine 2a, it's going to be 1 over sine of 2 times a half x. 2 times a half x is x. Now 1 over sine x is cosec of x. And that is what we needed to prove. We needed to show that this was equal to cosec x. Okay, job done. So, last bit of this question, I'll go on to a new page for it. We were told that the curve C has equation y is equal to log of tan a half x minus 3 sine x. Okay, so let's put that on the next page. Y is equal to natural log of tan a half x. Well, we've just differentiated log of natural half tan x minus 3 sine of x. And we're told to find the x coordinates of the points where dy by dx is equal to 0. Okay. Well, if I want to find out where dy by dx is equal to 0, I need to actually know what dy by dx is. So let's differentiate this first bit. We've got a half natural log of tan a half x. We've just done it. And if we couldn't do it, the answer was in part A. It's cosec x. So this bit becomes cosec of x. And this bit becomes 3 cos x. Because you've got sine, sine goes to cos, and you've got 3 of them. Now we're solving dy by dx equals 0. So we're actually solving cosec of x minus 3 cos x is equal to 0. Now if you think about what that actually means for us, well, cosec is 1 over sine. 1 over sine of x minus 3 cos of x is equal to 0. Well, if I multiply both sides by sine, I've got 1 minus 3 sine x cos x is equal to 0. Remember, I'm trying to rearrange this so that I've only got one trigonometric ratio. And again, go back to what they told us earlier. We know, because they've reminded us, that 2 sine x cos x is sine of 2x. So how can I make it so this is 2 loads of sine x cos x? We can do that by thinking of the fraction I can multiply it by. If I divided this by 3 and multiplied it by 2, and I'm getting this bit, yeah? So in a bracket, I'd need to take that factor out. In other words, I could actually say this is 3 over 2 loads of 2 sine x cos x. Because think about it. If I started with what I wanted, 2 sine x cos x, divide by 2 and times by 3, I've got what I actually have. So I know that what I've got there is 3 over 2 loads of that. Well, that's great, because now I can say that's 3 over 2 loads of sine 2x. Now I can start solving it, because I now know that I can move it to the other side and have 3 over 2 sine 2x is equal to 1. Have them equal. That would also mean that sine 2x, if I move the 3 over 2 to the other side, it'll be 2/3. I'd have to multiply by 2 and divide by 3. Well, that's great, because now nothing beyond P2. We're solving the equation sine 2x is equal to 2/3. Remember the steps to solve a trig equation once you've actually got the trig set up. Once you've got it as sine, cos, or tan equals something, we can solve it. The first step is we do inverse sine of that number, inverse sine of 2/3. This is where I go to my calculator. I've kept it there all this time, especially for this moment. So arc sine of 2/3. Except we need to be careful. That answer is already wrong, because right at the start of this question, we were told that it was between 0 and pi. So we know that this has to be also between 0 and pi, i.e. it has to be in radians. So shift, menu, and I want to put my angles in radians. There we go. Sine of 2 over 3 is equal to 0.7297 276562. Okay, great. Next step, draw your sine curve to remind you where everything goes. This is sine between 0 and 2 pi. Okay. We have a positive value 2/3, so it's going up here. There's my first value, the 0.7 bit that I've just calculated. This value, the second one, which is in our range, is 180 or pi radians minus that value, because this length from here to here is the same as that length. So I can now set up our two equations. I've got 2x, remember it's sine 2x that we're solving, that we've got here. So 2x is equal to 0.7297276 plus 2 pi n. Remember that it's repeated every 2 pi degrees. Radians, sorry. But I need to divide these answers by 2 because I need x. So x is going to be equal to, if I divide that by 2, I've got 0.36486 38281 plus 2 pi gets divided by 2 as well, plus pi n. There's my first equation. Okay. My second equation, 2x is equal to, is the value here. So I'm going to times by 2 again to get back to where I was. From the answer I had, this is pi minus my first answer. So I'm going to do shift pi minus my answer, and I've got 2.411864997 plus 2 pi n. So that means, again, I could work out what x is going to be. Divide both sides by 2. I'm left with 1.205932,499 plus pi n. Now, those two are two equations in boxes. They are the equations that will generate all of the solutions to this equation. However, this is where we go back to the definition. We were told our values have to be between 0 and pi, 0 and 180 degrees. The two values that work for us are actually the two we already have, this one and this one. But remember, even if you're only looking for those ones, you always work out the equation so that you know that you can generate these functions. We'll make a little note at the end. Between the values that we need, 0, x, and pi, we know that x has got to be equal to the 0.36, and then that 4 is going to get rounded up from here, because you can see the 8 is greater than 4, so therefore it's getting rounded up to 5. Radians is a little c. And the other one, 1.205, we asked for 3 decimal places. That 5 is going to get rounded up to 6, so 1.206. And make a little note, 3 decimal places. And there you have it. That's how we solve those questions. Okay, hopefully it wasn't too bad a test. If there's any questions, do let me know, and we'll go through in due time. Okay, well done, guys. Bye now. Bye now.